Yeah, sorry, I changed my title a bit because we have done some, I guess, recently done some work that might be interest to this audience. Okay, so basically, the title is more along the line of how do we understand strongly interacting systems in which the collective behavior can emerge, right? So I'm going to tell you two systems in particular. One is synchronization, as advertised before. Another one is more recent work that we have done in looking at the flocking, which is dear to my heart, some of you know. Okay, so without further ado, so in the last 20 years or so, my research focus has been mostly in biological systems, and there's a central question that we aim to answer in various systems in biology. Namely, how does living system process information accurately with noisy components and stochastic interactions, right? You can go from DNA replication, pattern formation, spatial order, circadian rhythm, temporal order, and learning and memory, sort of more complex form of order, and to flocking, something. I'll go back to this. So there are two questions we really want to ask is, what is the mechanism that allows it to do what it does, right? What they do. So the mechanism part, I'm not going to tell you too much about. But the second part is, how much does it cost to do for this system to do that? What is the energetic cost in particular, right? And the reason we want to ask this question is actually originated, we didn't ask this question, ourselves. This question is really put in front and center by this gentleman called Terry Hill. I don't know how many of you know about him. Terry is my hero. So this is the person that I think first developed this machinery of how you actually even think about dissipation in the biochemical network or kinetical system. So there's a couple of interesting concepts. I don't know if it's in this workshop has been mentioned. One is this called the cycle rule. Right? Basically, if you look at biochemical interaction circuit, like the simplest one, A goes to B, B goes to C, the bidirectional reaction. If you look at the reaction rate, if you multiply all the reaction rate in the clockwise, and if it's not the same as the product in the counterclockwise, the system is out of equilibrium, right? So that's essentially the same as detail balance being broken if that's not satisfied, right? As a result of that, if that is the case, then even in the steady state, you will have what people call the persistent current or cycle current, J, that is continuously exist even in the steady state. If you think about steady state, you think about something that doesn't change. No, underneath, currents are flowing all the time, but in circle, because you have to conserve concentration or density in each state. Now, together with that, then you have a thermodynamic driving force based on, because you have a driver current and with a chemical potential delta, thermodynamic driving force delta mu, then you actually get this free energy dissipation rate. So that's all I'm going to say about the technical background, right? I'm not going to say anything more about that. Okay, so we're going to use that in various different systems. And indeed we did. So basically our objective is really try to understand how now you can calculate for a particular, machinery in biology, mostly biochemical reaction network. You can compute the cost, right, in the steady state. And this particular steady state in biology doesn't do things randomly, have some intended function. So we always, the mainstream line of work that we have been doing the last 15 years has been try to relate the cost that we compute and the performance of those functions. Those functions can be different. For example, you can build a switch, biological switch, and you are interested in having an ultra-sensitive, very sensitive switch. So how much does it cost you to build a sensitive switch? The sensitive adaptation was mentioned some time ago, and you worry about how accurate adaptation has to be, and how much that would it cost you, and how fast you can adapt, and how much does it cost you, right? And so on. So I'm going to tell you more about that in biochemical oscillations. And this is just some of the work that we have done along this line of thoughts, right? So if you're interested, you can check those references. Now, so far, most of the systems that we have studied are spatially homogeneous, like a well-mixed bag of molecules. They interact with each other. They have multiple chemical states. You have to worry about transition between different chemical states, but they don't have any other structure to it, right? They're well mixed. So what about systems that consists of strongly interacting subsystems, within each of which consists of this chemical reaction or some interaction, but they communicate with each other? And because such a communication or interaction, certain emergent behavior arises, right? So I'll give you two examples. One is already published, namely synchronization of molecular clocks, which you heard a little bit about, molecular clocks. And this is published, so I'll go through very quickly, given the time. And the second example is actually something that we did just recently, flocking of active spins. So here's an archive paper that you can go check out. And something else that we have done, I'm not going to cover it in this talk. Okay, synchronization of coupled molecular clock. So what do I mean by that? You have seen this before. A clock, simplest, a single clock can be described by this, what I call Poisson clock, right? So you have these discrete states. You have this asymmetric random walk, if you wish, or what we call Poisson clock, right? It's basically, each process is a Poisson process. The reverse process is damped or is multiplied by a factor gamma, which is less than 1. And again, using the cycle rule, you see that the cycle rule says if gamma g in this particular cycle is equal to gamma of n, if n is not equal to 1, you dissipate energy. In the steady state, you dissipate energy for this model in a single clock level. But that's not what we're worried about. What we're worried about is, what about coupled clocks? Suppose you have two clocks that couple with each other, right? Then you have the problem that you have to think about interaction between different clocks. So for example, you can have exchange interaction, namely the total phase. So we describe the clock by phases, right, by their phase. If you interact with two clocks interacting with each other, the total phase is conserved, but they can exchange phase, right? So called phase exchange interaction. And such a phase exchange interaction is characterized by the frequency of how often do you do that and how strong the interaction is, E0. And you can see pretty clearly that, again, because the introduction of the exchange interaction, you also break detail balance at this local level. Even if you don't go around the full clock, you actually have a gamma of L, what we call the big gamma of L, local gamma that's not equal to 1 because of the existence of such exchange interaction. Okay, so you have two sources of irreversibility. Now, because of that we can study the whole system based on the exchange interaction that are characterized by the two control parameter, the frequency of how often it occurs and how strong it occurs, E0, right? And you see the synchronization transition happen in this parameter space through a second order phase transition, right? So then we ask so this is the mechanism part. That we're going one step beyond that. We say, what about the energy cost? At each point here, it costs you something, dissipation rate, right? We can compute it by actually we can not only compute it, we can decompose it into what we call precessive energy cost, which means that each individual clock will cost you something to go around, and exchange energy, right? The energy that used to push the exchange interaction. And the exchange interaction is the most interesting part. That would depend on omega and E0. And if we go along a line that was a given E0, and look at the dependence on omega, then you plot the order parameter, which is synchronization order parameter, versus the dissipation along this line. You get something that you typically see in critical phenomena. It's basically your order arises only when you're driving, in this case characterized by the dissipation rate, is over some critical value. And that critical value depends on, always finite, but it depends on where E0 is. And the envelope of that line tells you something interesting, that with the same amount of, with a given amount of dissipation, what the maximum order you can create. So in other words, this is the optimum design line that allows you to achieve the same amount of this synchronization characterized by R with the smallest amount of energy dissipation. And that in this phase, in this control parameter space, omega versus E0, that corresponds to the dotted line. In other words, if you have this amount of energy, they should go, so the relation between omega, capital omega and E0 have this following line that basically corresponds to what we call the optimal design line. Again, I don't want to draw too much into this. This is all published. I want to go back to why we're doing this and what is impacting biology, right? So the system has been introduced. The cyanobacteria circadian clock is a well-studied system, Chi-ABC system. And it's really the field really takes off because of the sort of the system can be reconstituted in vitro in the test tube by mixing Chi-A, Chi-B, Chi-C in a certain proportion, and you add ATP and it starts to oscillate, right? But you have to see Chi-C really forms a hexamer. So it really is an individual clock, molecular clock. So what happened in the Chi-C hexamer is that from 6 a.m. to 12 p.m., the clock moves by adding phosphorate group to residue, right? One at a time. So there's 6 to 12, and to 6 p.m., it becomes 6 sp, the two sides. And back to 12 a.m., midnight, and all of it's gone, right? So it's really a molecular clock that operates on a molecular machine, right? So the number is 1. The molecular number is, maybe if you wish, number of molecular state is 12. As such, the noise is huge, right? You can imagine. So if you just let it alone, it will asynchronize. And if you average over a soup of Chi-C hexamer, you're not going to get oscillation at all. So it's critical, absolutely critical, to think about this system by using synchronization as a guidance, right? So how does it synchronize? You have this two hexamer sitting around. How do they talk to each other, right? So again, I won't go into detail, but what so happened is that people discovered once in a while, this hexamer actually blows up, actually dissolve and recombine to another hexamer. So they exchange partner. This is so-called monomer exchange. So by using such monomer, another related puzzle in the whole field, right, is that people not only can actually look at the individual, measure the phosphorylation level, they actually can measure the ATP consumption per hexamer, per monomer, per unit of time, for 24 hours, right? And you would imagine that if a monomer goes through its cycle by phosphorylate 2 residue and dephosphorylate again, 2 ATP is the minimum you need, right? So they actually went ahead and measured it. It turns out 16 ATP are hydrolyzed per Chi-C per day. So where did the other 14 ATP go, right? So our claim, okay, so I won't go any further, is that those, at least a major part of those 14 missing ATP is consumed to make them synchronize, right? So we have some specific algorithm, mechanism that we actually developed, in which we can compute the exchange. This is the exchange rate. So because the monomer shuffling, that's corresponds to the exchange rate, and we can compute the amplitude of the overall collective oscillation, right? The order parameter, if you wish. And indeed, what you find is that you need to have this monomer shuffling to over some critical rate in order for you to see any amplitude, finite amplitude at all, whereas the period doesn't get changed much. And you can say, using the same model, you can compute the dissipation rate versus the exchange rate, right? And this is where you see the baseline. One of the baselines is 2 ATP here, right? But as you see from our theoretical work, if you introduce exchange interaction here via monomer shuffling, you actually have to cost you additional one, depending on the interaction strengths. And this is the 14 ATP that I observed. So as you see, in order to create the order dotted line here, you actually need to dissipate more and more energy depending on the ES, the exchange interaction. And it's not very far from what people observe, 16. But at least it gives you one direction to see where the missing ATP consumption has gone to. We firmly believe it has at least part of it, if not a major part of it, has gone to make synchronization happen. Okay, all right, let's move on to the next This is added bonus. We just finished this a couple of weeks ago. So thermodynamics of flocking of active spins. What do we mean by active spins? The active spin Ising model was actually developed by Solon at Turia at the 2013 and 2015. Basically, it's a very simple microscopic model that actually have flocking. The original VCheck model that we work on has continuous symmetry and is working off-lattice system, right? It's not very good to doing this kind of setting. So we chose to do on the active spin because it's a very simple model. So what it is that each spin has a speed, either spin up or spin down. So depending on the spin that it has, it can either bias to go left or go to right. For example, the plus spin will bias to go to the right, to the right, and the negative spin will bias to be going to the left, right? Bias is characterized by epsilon. That's one key parameter, right? Once you are on a site, all the spins are interacting with each other through some mean field Hamiltonian. That's purely equilibrium mean field Hamiltonian given by some very simple form of mean field Ising model, basically. The system is not exactly manageable, totally manageable, but it's actually closer than off-lattice symmetric continuous symmetry model because it still has 2 to the n, 2L times n degrees of freedom, right? So if you imagine you have to calculate each transition along this high dimensional space, it's almost impossible, but it can be done. So which is what we, but just to give you an idea why the system breaks detail balance, right? So if you look at the system in the simplest model possible, only have two sides, L equals 2, and N equals 2. You only have two particles, right? Two spins. Then you see that the system, if you follow the cycle by alternating between flipping and hopping, moving to the next side, you find that you form this cycle, all right? You form the cycle, you find the gamma, remember our friend, the cycle rule gamma is actually not equal to 1. Even when epsilon equals 0 is actually not equal to 1 because of this e to the minus beta. So only when, I guess, beta is 0, zero temperature or infinite temperature and epsilon equals 0, that actually go to 1. Anyway, so in other words, energy is continuously dissipated to maintain the non-equilibrium steady state. I didn't tell you it's flocking state. I tell you it's non-equilibrium steady state. The steady state can be either non-flocking or flocking. And so we're trying to find out is that how much energy does it actually cost you to actually form the coherent flocking state, right? Just like we did in the synchronization case. All right, this is some kind of an energy dissipation rate. How we computed it, you can do that. I show you, if you're interested, you can go check out the archive paper. But what we find is the following, is that again, very similar to the synchronization case, there's a critical line here that corresponds to the transition from, so the two key parameters we are doing is E0, the coupling.
Sorry, you have like 1 minute left, right? But you can also continue a bit longer. You have like 1 or 2 minutes left from the official time.
Oh, okay. What's my official time?
I mean,
okay. All right.
If you think about 20 minutes. Yeah.
Okay. All right. So the critical line here is between the non-flocking state v equals 0 and the flocking state, which the speed is bigger than 0. And along that, in that same parameter space, you can compute again, just like the synchronization case, the dissipation for alignment dissipation. So the dissipation comes from two parts. One is actually a physical motion, the actually hopping itself, when epsilon not equal to 0. Another one is the alignment energy dissipation rate here, right? So that again, we use the same kind of approach. We look at how does it, if you look at for a fixed epsilon, how does the dissipation, if you change E0, how does the dissipation control the flocking order, characterized by the order parameter, E3, right? But this is what we find. So this is the blue line. So you see there's a finite value here that corresponds to the transition. But if you look at the red lines, what interests us, the red lines is the dissipation rate for the alignment, right? There's an additional term corresponding to motion, which is somewhat trivial. But the dissipation corresponding to alignment has a peak here. And not only has a peak, it actually has a peak with a cusp. When n goes to infinity, we can show that it's actually a finite discontinuity in the first derivative, right? So there's actually singularity there. So we show that by actually looking at the two-side, the simple model, two-side model, which you can solve at least analytically, numerically in the finite n case, but numerically, analytically in the n equals infinity case. And the dotted red line here is actually this result. And on top of it is the result we get from the original model, right? This is a two-side model. For original model meaning that multiple sides, many sides. And they actually agree pretty well. More importantly, we're actually able to show right at the critical point, the dissipation depends on the order parameter, which have a discontinuity, right? In the first derivative at least. So that's where the cusp really comes in. Okay, this is my last slide, really. So why are we doing this, right? So this is a good exercise to understand the energetic cost of this. But stepping back is that what is the use of having energy dissipation? Well, you need necessarily condition to have dissipation. But if we only just want to minimize dissipation with a given performance, in this case measured only by, if we only measure by the order parameter V, then there are multiple choices of E0 and epsilon that we can choose. For example, here, for a flocking velocity of 0.8, each line corresponds to what we call equal speed line, right? You can have multiple choices of E0 and epsilon. Let's look at the red line, right? And the first point corresponds to A corresponds to a large E0 and small, relatively small epsilon. And here on the B side corresponds to a very large epsilon, hard driving by motion, but heavily biased motion versus this relatively small E0. So let's look at A and B. What happened is from between A and B, the dissipation, total dissipation actually increases. So you would think that, okay, why don't I just save my energy by using the choice of a large E0, very stiff interaction, ferromagnetic interaction, but slow motion, slow biased motion, right? Small epsilon. So maybe that if you only consider velocity, speed of the flocking, that may be true. But then the flock also has to change direction, right? If you look at the susceptibility of the flock, by characterize the sensitivity of the system by basically say, this is just susceptibility, right? At the h equals 0 point, what you find that the energy you put in here actually is used in the system, the flocking system, to enhance its susceptibility. So it's more fragile, more rigid, not less rigid. So you can change direction much easily, right? So that's just sort of a food for thought that there's apparently an energy, speed, and sensitivity trade-off in flocking. And this is my last slide. Sorry for running over time. I don't have to, I mean, you can read this, so I can just finish my talk here. Thank you.